All right, so as I mentioned earlier, again, we're looking at energy and the work done. That work is transferring energy. And one of the things that we're first going to look at is that when you do work on an object, one of the things is you can do is you can speed it up. You can make it move. And so what we're going to look at is something called kinetic energy, all about movement, and the work energy theorem. And what it's saying is that when you have kinetic energy, which I call EK, E for energy and K for kinetic, that is the energy an object has because of its motion. I believe kinetic is a Greek word for motion. All right, and so we have a formula where EK, the kinetic energy, is your mass mv squared divided by 2, where m is your mass, v is your velocity. Or instead of dividing by 2, you can multiply by a half. Exactly the same thing. All right, so we have mv squared divided by 2. So if you know the mass and you know the velocity of an object, then you can figure out its kinetic energy. Now with this formula, the other thing is if your v value is 0, you don't have any velocity, means you have no kinetic energy. All right, so I get to my first example with my whale. So I have a whale, massive whale, has a mass of 1,500 kilograms. That's 3,000 plus pounds. Is swimming with a speed of 6 meters per second. Find the kinetic energy of the whale. All right, so again, this is example 1. We have our whale, which has a mass of 1,500 kilograms. All right, and it has a velocity of 6 meters per second. All right, so again, you have to be in our standard units where velocity has to be in meters per second, not kilometers per hour. And again, your mass has to be in kilograms. And so if I'm finding the kinetic energy of our whale, well, I'm going to use my formula there of EK is equal to mv squared and divide by 2. All right, so if I substitute in my values, I have my mass, which is 1,500. My velocity, which is 6, squaring it, divide by 2. And of course, when you're following these formulas, always got to follow BEDMAS. There's my math teacher experience coming in. So we got to do that exponent first. All right, so we got 1,500. Again, 6 times 6, that's 36. And then, of course, we have divide by 2. And so now I can do it all in one step, where if I have 1,500 times 36 and then divide by 2, the whale has a kinetic energy of 27,000 joules of energy. So again, the bigger you are, more kinetic energy you have, or the faster you go, you can have a lot of kinetic energy. And of course, if you have both, well, then you're going to have a ton of kinetic energy. All right, now we get to B, same whale. How fast would the whale be swimming if it had 100,000 joules of kinetic energy? All right, so how fast would that happen? Because we know with 27,000 joules of energy, it's going 6 meters per second. So obviously it's going to be going quicker. All right, so in this case, same whale here, but now our kinetic energy is 100,000 joules. The mass of the whale has not changed. It is still the 1,500 kilograms. All right, so once again, I'm going to sub into the same formula. We're just going to find a different value. And so our kinetic energy is initially 100,000. All right, we have our m, which is 1,500 times v squared divided by 2. All right, so a lot of ways to work with this formula. The first thing I'm going to do is I got a 1,500 divided by 2. I'm going to calculate that or simplify that. All right, so 1,500 divided by 2, I know is 750 times, of course, my v squared. I do that so that I can just get one number on that side, and so that I can divide now by my numerical coefficient, which is that 750. Again, there's lots of ways to solve this. I just like to do it the easiest way, given that I've taught math for 20 years. All right, so those two divide each other out. And so I just have a v squared. Now I got to figure out what 100,000 divided by 750 is. And let's see here, get my trusty calculator out, and I get to 2 decimal places, I get 133.33. And then, of course, the last step is to get rid of my little 2, the exponent on the v, which I'm going to take the square root of both sides. And now the velocity of my whale, I know it's going to be bigger than 6, right? Because there's more energy there. And let's see, I take the square root of 133.33, and I get 11.55 meters per second squared. All right. Now, the work energy theorem essentially says is that the total work on an object is equal to the change in its kinetic energy, which in this case, our object is at rest, and so all the kinetic energy went in, or all the work energy went into making it go faster. Now, we'll look at example 2. So again, I just want to write up the old work energy theorem, is that again, if you put some work into an object, you're going to change its kinetic energy. Now, in math and science, to show a change, often a Greek letter delta is used. There is a change in kinetic energy. And since an object's mass will not change, the only thing in that formula that can change is the velocity. And so what you're going to have is a final kinetic energy, so EKF, I guess, subtract what you started with. So we'll have an either or a 1 for the initial kinetic energy. And again, as I said, the mass will not change, and so our formula would simplify down to mass times VF squared divided by 2, subtract mass times VI squared divided by 2. So again, essentially what it's saying is if you put work into speeding an object up, maybe it's at rest, maybe it's already moving, but again, you're going to change the speed if you put positive work into it. If you put negative work into it, you can slow it down. All right, so now we get to example 2 with a police car. A police car, which is 2,400 kilograms, must be a van, at rest, receives an emergency call, and so the driver starts in motion. The increase in speed from rest results in 300,000 joules of work done on the car. Determine the police car's speed. All right, so again, I've read the question here. I know the mass is 2,400 kilograms. All right, now at rest, our object, police car there, must be sitting, and so its VI is 0. Its VF, we don't know how fast it speeds up to, but we do know, again, the mass is 2,400 kilograms, and the work done on the car, lots, 300,000 joules of energy. Now, again, I'm going to use my formula up here, except for it's going to simplify because, again, this object's at rest. And so what we're looking at is if you have work is our final kinetic energy minus our initial kinetic energy, I can absolutely, or I can simplify this and actually get rid of my initial kinetic energy because our object's not moving. It's at rest initially. All right, so I can substitute into my formula and then I know that 300,000 joules of energy are applied by the motor to the vehicle. All right, we have our EKF, our final kinetic energy, which would be mass times VF squared divided by 2. All right, I guess I could have substituted in for math there, or mass. Let's see if I can fit that in there. Let's go with that. Yeah, there we go, 2,400 kilograms. Again, I'm going to simplify where I have 2,400 divided by 2. Well, that is going to be 1200 VF squared. All right, so again, I still have my 300,000 joules of energy. And just like I did before, I'm going to isolate for VF. I'm going to divide by 1200 on each side. All right, and so let's see here. So, well, those 1200s divide each other out. And so I have a VF squared, 300,000 divided by 1200. I end up with, let's see here. Let's double check that. Oh, I end up getting 250 right on. And again, to get VF squared by itself, I'm going to have to square root both sides, as I did before. And so the final velocity of my car, take 250, square root it, and I get 15.81. And again, because we're dealing with our standard units, we have ourselves at meters per second. All right, so there's, again, another example of our velocity changing from rest. Now, we get to the next one, a little bit different. Different look at things. Let's see here. The old Archer. Whoops, probably should have got rid of that. All right, so example 3. Oh, that's wet. Don't want to rip my marker. All right, so example 3, we have, again, I always like to read the question, figure what we got. We have an archer, pulls back her bowstring loaded with a 50-gram arrow, and then releases a string. If the arrow leaves the bowstring at a speed of 80 meters per second, calculate the work done on the arrow by the bowstring. All right, so again, the mass is 50 grams. Now that is a problem because that is not in our standard units. And again, there is 1,000 grams in a kilogram. And so if I divide by 1,000 here, I end up with 0.005 kilograms. Okay, now my arrow, when it's initially starting, is nothing. There's no speed on an arrow, thank goodness. Otherwise, it'd be tough to shoot it. VF, though, we know is 80 meters per second. All right, now, and what we want to look at is calculating the work done on the arrow. All right, now, let's see here. So, again, using our work energy formula, we have W is equal to our change in kinetic energy. But again, because all of our energy is going, there is no speed initially, there is no kinetic energy initially, and so all of our work is going into the final kinetic energy, because again, our initial kinetic energy is 0. Put that right here. Therefore, EKI equal to 0. All right, so again, our work is equal to EKF. Well, that's MVF squared divided by 2. All right, so I'm going to substitute my values. And so again, our mass, very small in our standard units, 0.05 kilograms. Our VF is big, it's 80 squared, and divide by 2. And again, I must follow Bedmas. And so I've got to do 80 squared first. I believe that's 6,400. I think that's right. Let's see here. 80 squared. Oh, clear. 8 times 8. Yeah, 6,400. Got to trust myself here. All right, there we go. All right, and let's see here. So then I find the work done by the arrow, or done by the bow on the arrow. And let's see here, I got a 0.05 times 6,400 divided by 2. And I end up with 100 160 joules. Again, a very small amount of energy, because when you're looking at the energy of an object, two things matter. It's the mass and the velocity. So even though this object is going very quick, it's not very big. And so that's why it doesn't have as much kinetic energy as, say, our whale, who wasn't going as fast, but yet a massive, massive object. Now, get to part B. It says, what is the magnitude of the force the bowstring exerts on the arrow if the force is applied over 12 centimeters? So that's a very small area, but again, that's how a bow works. So your delta D is 12 centimeters. Again, there's a bit of a problem here because not in our standard units. Now there is 100 centimeters in a meter, and so if I divide by 100, my delta D, or my D, however you want to look at it, is 0.12 meters. Now, I know how much work was exerted. I'm looking for the force. All right, now the arrow and the string, the distance, are moving in the same direction, so I can use my formula. W is equal to FD. All right, and again, I don't need the cos theta because the distance and the bow is applying the force in the exact same direction. All right, so I apply my work here is 160 joules. My force, that's what we're trying to figure out here. And my distance, it's over 0.12 meters. And of course, the last thing now to figure out my force is divide by my 0.12 here. So again, we're intertwining our formulas that we had earlier. Those divide each other out. And the force, let me see, 160 divided by 0.12 is, to two decimal places, 1,333.33. And again, we're in standard units here, newtons. So there we go. So again, it's looking at a different type of energy, which is called kinetic energy, which is the energy you have if a mass is moving. And we can apply some work, which is again transferring energy, to make something move. All right, in our next class, we are going to look at different types of energy and the rates of using energy. But for now, that's just a little introduction of how we use energy to get things to move. We apply forces to make that happen, like we did with the bowstring on the arrow. And again, we're going to look at different types of energy later on this week.